In normal computers, a bit can only be in one state at a time, either a 0 or a 1. So if you had 2 bits, they could be in one of 4 possible states: 0, 0, 0, 1, 1, 0, or 1, 1. Let's say each of these states represents a number: 0, 1, 2, or 3. If we want to do a calculation, for example raising 7 to the power of one of these numbers, we can only do it for one state at a time. In this case, 7 squared, and so we get the answer 49. Quantum computers consist of qubits, which also have 2 states, 0 or 1. But unlike a classical bit, a qubit doesn't have to be in just one state at a time. It can be in an arbitrary combination of those states, a superposition, if you will, of 0 and 1. So if you have 2 qubits, they can exist simultaneously in a superposition of 0, 1, 2, and 3. Now when we repeat the same calculation, it will actually perform the calculation for all of those numbers at the same time. And what we're left with is a superposition of the different answers: 1, 7, 49, and 343. If we add another qubit, we double the number of possible states. So with 3 qubits, we can represent 8 states, and thus perform 8 calculations all at once. Increase that number to just 20 qubits, and you can already represent over 1 million different states, meaning you can simultaneously compute over 1 million different answers. With 300 qubits, you can represent more states than there are particles in the observable universe. This sounds incredibly powerful, and it is, but there is one very big catch. All of the answers to the computation are embedded in a superposition of states. But you can't simply read out this superposition. When you make a measurement, you only get a single value from the superposition, basically at random, and all the other information is lost. So, in order to harness the power of a quantum computer, you need a smart way to convert a superposition of states into one that contains only the information you want. This is an incredibly difficult task, which is why for most applications, quantum computers are useless. So far, we've only identified a few problems where we can actually do this. But as luck would have it, these are precisely the problems that form the foundation of nearly all the public key cryptography we use today. In 1994, Peter Shor and Don Coppersmith figured out how to take a quantum Fourier transform. It works just like a normal Fourier transform. Apply it to some periodic signal and it returns the frequencies that are in that signal. Now this may not seem particularly interesting, but consider this. If we have a superposition of states that is periodic, that is, the terms in the superposition are separated by some regular amount, well, we can apply the quantum Fourier transform and we'll be left with states that contain the frequency of the signal. So this we can measure. The quantum Fourier transform allows us to extract frequency information from a periodic superposition, and that is going to come in handy. So how does a quantum computer factor the product of 2 primes much faster than a conventional computer? I want to explain this by first walking through a simple example with no quantum computer required, and then I'll show how a quantum computer could execute this method even for a very large number in a short period of time.